This time we are going to deal with the output analysis. The previous chapter was dealing with the output analysis where we want to estimate of the absolute performance of a system design. Now we can also use the simulation to compare alternative system designs, right? So let's just say there is a certain decision variable that we need to decide on in a system, and we are trying the simulation methodology to compare the performance of alternative systems with these different values assigned to the decision variable. And we want to compare this system relative performance. So which system is better on the other one? So we are going to make a benchmark of the systems. In that case, the output analysis of the simulation results is dealing with the estimation of the relative performance. So if we are comparing alternative system designs, then this is going to be the estimation of relative performance metrics, not the absolute. The absolute performance is estimated for a single system design only, without any purpose of comparison. So we are going to compare the alternative system designs, and actually in the end of this course, we will only be able to learn the comparison of two different system designs. If you are interested in how you can compare multiple system designs, you can review your statistical knowledge about ANOVA methodologies. With the ANOVA technique, you can compare alternative multiple system designs, but you can simply use a t-test to compare two systems. But to compare alternative systems, you use an f-test. But you can always compare the multiple systems 2 by 2 with each other. I mean, you can always say that there is a standard and there is a challenger system, and whether which one is better will be compared with the next challenger, right? So it always goes like this, like you are playing Street Fighter or Mortal Kombat, okay? You are always playing against the next challenger. So just like that, you can compare two systems and the winner will be compared with the next challenger system. And by that analogy, you can compare multiple systems in any way. And we are going to make a review about the statistical comparison techniques. And then we are going to talk about two things: the independent sampling and the correlated sampling. If you remember from the statistics course, when you run a two-sample hypothesis test and these samples are correlated with each other, you were using a different type of t-test. Remember, you were subtracting one sample from the other one, and instead of applying a two-sample t-test, you were applying a one-sample t-test when we have correlated samples in two-sample t-test. This is exactly what we are going to do here as well. We are going to use the correlated sampling idea to reduce the variance of the simulation results to gather much more reliable results. But first, we need to understand the independent sampling concept. Then we are going to explain correlated sampling and how it can be helpful to increase the reliability of simulation results. As we have said previously, using simulation as a basis of decisions requires the comparison of simulated performances of alternative system designs. For example, imagine a bank system under two different Q disciplines. Imagine a banking system where it behaves fairly for every client, and imagine a banking system where they give priorities in the queues for their specific customers. For example, if the customer has a large amount of money in their bank account, they always take them in front of the queue. Actually, this is exactly what they are doing in any way. I mean, if you go there to take a loan, or if you are just going to deposit a large sum of money, in that case, you are always going to get in front of the queue, okay? And we have two different Q disciplines here, right? If we want to compare which system performs better, then we need to run a simulation of these two alternative systems designs or two alternative configurations, and we can measure the performance metrics. Or imagine a call center with two different representative working schedules. Let's just say you want to determine an optimal working schedule for your call center agents. So at which hours, how many call center agents are going to work? Now you can find the solution with an optimization technique. However, how can you do that while the inputs are random, right? I mean, you can develop a linear programming model if your inputs were deterministic. But if your inputs are random, then you are going to run an optimization with simulation approach. Therefore, you need to combine the optimization methodology with the simulation methodology here. So these kind of things that we want to determine, such as the working schedules of the call center representatives, it is basically something that should be optimized by the results of a simulation. And imagine an inventory system which allows or forbids back ordering. So if you have taken manufacturing planning course, in that course you have heard about the inventory systems. You know, in some inventory systems we allow back ordering, which means we can make sales which we are not going to be able to deliver. This is called back ordering, or in other words, you are basically postponing the demand of the customer. You are postponing the delivery time of that customer. This is called back ordering. You get the money, but you do not deliver the goods at that moment. You are going to deliver them later, which is going to end up with a negative inventory level. In that case, usually when you allow back ordering, the costs of these inventory systems can further be reduced. When you allow something, even it seems costly, when you allow something, it always helps you to reduce the cost because it is just an allowance. It is an option to use. Allowing something never increases the cost. Even the back ordering costs are large. So it is an option which you can use. Therefore, you want to make a comparison. If I allow back ordering up to a certain level, how my costs are going to decrease in my inventory system. And you can again run a simulation if the demand is too stochastic. If the demand follows a probability distribution, if the demand is not deterministic, and in most systems it is not. I mean, nobody can actually predict the actual demand if the system does not work on a pull basis. In push types of manufacturing systems, we always observe random demand. And when we have random demand for these kind of inventory systems, simulation can be a very useful approach to solve the problems. So let's just say the analysts want to compare these alternative system designs. Now, in order to do that, we need to be simultaneously running the simulation for all of these system designs, and we are going to compare their performance metrics at the same time. Okay? But we will just focus on the comparison of two alternative system designs. Now, let's just say we have a performance measure such as the expected queue time. So the expected time spent in the queue by the customers. This is my performance measure, right? So let's just say theta K is the expected queue time for system K. And I have two systems only, system 1 and system 2. So I apply a change of policy, or I change the queue discipline. Or for example, in that second system, I train my employees so they can perform better. I want to see the difference. You know that if theta 1 is less than theta 2, we can say that the system 1 is better. If theta 1 is greater than theta 2, then system 2 is better. Why? Because the less the expected queue time is better for the client's satisfaction, right? So if the expected queue time is less, then they will be more and more satisfied, basically. But if theta 1 and theta 2 are the same, in that case, we say that the comparison is inconclusive. So we cannot say which system is better in the expected queue time. Now, I am just going to compare these two system designs with simulation. But you know, in the end of the simulation, I will not be able to find the exact values of theta 1 and theta 2. I'm going to get estimations of them with a certain confidence levels. So I'm going to make a comparison of these two estimates with a t-test, right? To prove a hypothesis or not. So I will just say that, for example, my null hypothesis is theta 1 to be equal to theta 2, and my alternative hypothesis is theta 1 is not equal to theta 2. And I'm going to apply a t-test for that with the simulation. However, at this point, we need to say that there may be two different statistical techniques that I will be able to use, which are called independent sampling and correlated sampling. In independent sampling, alternative system models are run with different streams of random numbers. and maybe in different numbers of replications. So this means when I test the first system, I can do 10 replications, and in the second system, I can do 20 replications. It doesn't matter how many replications I run, and in all of the replications, either in the first system or the second system, I always use different streams of random numbers or different random number sequences. In that case, the sampling will be an independent sampling. Okay? If the random numbers are different in all replications, no random number sequence of any replication of the first system or any replication of the second system will be the same. They are totally going to be different in independent sampling. And the number of replications in each system design can be different as well. Now, in the correlated sampling, both alternative system models are run in the same number of replications, and in each replication, I use the same stream of random numbers. For example, what random number sequence I use for the first replication of the first system will exactly be used for the first replication of the second system. So the first replications of the both systems are going to be simulated with the same random number sequence. And we call this technique common random numbers technique. So why do I do that? Why I am using the same random number sequences in the respective replications of each system design? Basically, I am trying to create the same scenario. Now, if I do independent sampling, because of the random number sequences are different, under the same conditions, we are going to observe different random events occurring, and therefore, there will be additional variation coming from the random inputs when you are comparing two systems. But let's just say you want to compare a supermarket where you are either going to work with 2 cashiers or 3 cashiers. Now, if you apply the same scenario in the simulations of these alternative system designs, for example, the arrival times of the customers are going to be the same. So you are basically trying to leave this exact the same day in the supermarket, but you are trying it with a 2 cashier in one of them and 3 cashier in another one of them. Now, maybe you are always imagining the same situation like this, right? I mean, what if I have chosen the other decision? So in real life, it is impossible to answer this question, right? For example, instead of taking the municipal bus, public transportation, what if I have chosen to take the shuttle from university? So you have two alternatives here. Either you take the shuttle or you take the bus, but you do not know which one is going to reach there first. And when you take one of them, you will not have any idea about the other one, right? I mean, unless you call somebody in the other bus. But when you make a decision in real life or test it, you do not know what's going to happen with the exactly same conditions the other way around.